Hi everyone. So this is a quick video to help you review the lesson on linear systems, which is lesson number 5. Um, so we have been solving a system of equations, right? We've had maybe a system where there are two equations or three equations, and we've been trying to write it in the form of AX equals B, right? Where A is your coefficient matrix, X is your variable matrix, and then B is the matrix on the right hand side. So now, one important thing that we can do is classify such a system. So there are two main different ways in which this system can be classified. And the first one is known as homogeneous. Okay, so what does homogeneous mean? This is the scenario when the right hand side vector is simply the zero vector, right? So basically, everything on the right hand side of the equality sign for each equation will just be zero, okay? And then the other one is non-homogeneous, which basically means that you have a vector on the right hand side which is not the zero vector. So there's at least one equation where the right hand side has a non-zero number. Okay, so these are the two main ones. And now we want to first think about the solution of a homogeneous linear system. Okay, so let's consider an example. So if we have a homogeneous linear system, the book gives you a very nice result over here, which says the following. So here's a result which says that AX equals 0 has a non-trivial solution. So what does the word non-trivial mean? So here, the word non-trivial is important. Well, trivial is the scenario when you take your x vector or your variable vector to simply be the zero vector. And if you think about it, that is always a solution of a homogeneous system, right? Like if you take any matrix A and if you multiply it with the zero vector, you will, of course, get the zero vector, right? So this is always a solution. So this is known as the trivial solution. Okay, so what we are looking for is a scenario where something is non-trivial, right? Because that's the more interesting case. This is always going to happen. You're always going to get a trivial solution. So if you want a non-trivial solution, then that happens only if, so if and only if the equation has at least one free variable. So if the system has at least one free variable. Okay, so if there are no free variables, then the only solution that you will have is going to be the trivial solution. So you have to keep that in mind. So hence, if no free variable, then we only have a trivial solution. Okay, so that's an important thing. So now let's quickly look at an example. All right, so here is the system that I want to work with. So I have 3x1 plus 5x2 minus 4x3 is 0, right? So since this is a homogeneous system, I will have zeros on the right hand side. Minus 2x2 plus 4x3 is 0. And then finally 6x1 plus x2 minus 8x3 is 0. So you can clearly see that this is a homogeneous system, right? Because you have your matrix A over here from this, which is 3, 5, minus 4, minus 3, minus 2, 4, 6, 1, minus 8, right? And then, of course, your variable matrix is x1, x2, x3. And you can see that this basically means that your B vector is nothing but the 0 vector. So this is a homogeneous system, okay? And now we want to solve this. So what would you do? Well, in order to solve, I think all of you are familiar by now, you work with the augmented matrix, which is A, and then the 0 vector in this case, because your B vector is the 0 vector. So you will simply have, again, the A matrix, 3, 5, minus 4, minus 3, minus 2, and then 4, 6, 1, minus 8, and then you have 0, 0, 0 over here. So that's your augmented matrix. And then what will you do? Well, you will try to take this to the REF form, right? So you want to convert to REF from here. So I would pause the video here for a second and try to do that. Okay, so that is an exercise for you. So please try to think about how to get this, or what will the REF look like. So I'm going to eventually write what it looks like. So it's going to be of the form 3, 5, minus 4. Remember, it's REF, so I can have the 3 there. I don't need it to be a 1. All I need is the entries below the first non-zero entry to be 0, right? So it's an upper triangular matrix, and then eventually I have 0 here, and 0, 0, 0. So if you carefully observe, since if you do any row operations, and since all of these are all zeros, you will still remain with zeros throughout. So basically what you need to do as an exercise is to see that this converts to this when you try to do row operations, right? So make sure that you do that exercise. But now, what is that you observe? You see that you have a row of all zeros, right? So a row of all zeros tells you that x3 is a free variable, right? That's the important conclusion from there. And so how can you write the solution? Well, if we read through all the rows, then the first one tells you that 3x1 plus 5x2 minus 4x3 is 0. And then the second one tells you that 3x2 is 0, which actually gives you information about x2. It says that x2 is 0. And so if you use this back into the first equation, you actually get that 3x1 minus 4x3 is 0, which then tells you that x1 should be 4x3 divided by 3, right? So I took the 4x3 to the other side and then divided through it by 3. So that gives me x1 in terms of x3. So that's done here. X2 is 0, so that is also done, and x3 is just going to be equal to x3 because that's a free variable. And so eventually, how does your solution or matrix look like? So remember, it's x1, x2, x3. So you have 4 over 3 x3, 0, and then x3 itself. Now, if you recall the parametric vector form, remember, because I have a free variable, I can write this whole thing in terms of one parameter, which is x3. And so finally, my solution is going to be equal to, so what do I get? I get x3 times 4 over 3, 0, 1. So that's my solution. Okay, and you can clearly see that this is non-trivial because you're allowed to take x3 to be anything, right? That's a free variable. So you do get infinitely many non-trivial solutions. Is that okay? So that is how you solve, or that is how the solution to a homogeneous equation looks like. And again, please do make sure that you have this important result in mind, that the trivial solution is always a solution, right? Because if you multiply the zero matrix to anything, you get the zero matrix. But if you want something interesting and non-trivial, then you want a scenario where you have at least one free variable. Okay, so that is what we have here. Okay, so that's it. That is the solution of this homogeneous system. So now let's also, and of course, if you want, you can label that this is trying to be written in the parametric vector form. Okay. Now, of course, the next interesting or the more complicated case would be if you have a non-homogeneous system. Okay, so if we work with a non-homogeneous system, so then let's take another example. This is again from the textbook. So for non-homogeneous system, remember that the right-hand side vector is not a zero vector anymore. So here's an example. Suppose we take AX equals B, where A is the matrix. So remember, instead of giving you a system of equations, I'm giving it to you in the matrix vector form or the matrix equation form. 3, 5, minus 4, minus 3, minus 2, 4, 6, 1, minus 8. So if you actually closely observe, this is exactly the coefficients I had in the homogeneous case, with the only difference now being that my B vector will be a non-zero vector. So let's say it is 7, minus 1, minus 4. So now, if you did pause the video before and went through figuring out the REF version of this matrix, then, or the augmented matrix, then you can go to that step and then also figure out the RREF, right? Because remember, we want to figure out what is the solution here. Okay, so now let's again work with the augmented matrix. Okay, so that will be A followed by, so this minus 3, minus 2, 4, 6, 1, minus 8, and then you augment it with the B vector. Again, I would pause here and do the exercise that convert this to RREF. You have already gone to a certain distance because you did REF with the first case, the homogeneous case. In this case, of course, this will be non-trivial now. Like you will have non-zero numbers here when you do operations or row operations, so you have to be more careful. So you have some idea about how to do this, but I would again pause the video and do this exercise. So convert this to RREF. Okay, there'll be a little calculation involved, some fractions involved, not too complicated. But what you will eventually end up with is the following: 1, 0, negative 4/3, and then you have 0, 1, 0, 0, 0, 0, and then the right hand side looks like minus 1, 2, 0. So what does this tell you? Well, we again, if you closely observe, end up with a row of all zeros, which then basically means that you have a situation where x3 is a free variable, right? And now let's write the other things. So you get from the first row that x1 minus 4 over 3 x3 is equal to minus 1. So you can write x1 in terms of x3. So it's 4 over 3 4 over 3 x3 plus, or not plus, minus 1, right? Minus 1 was already there on the other side. And then the second equation simply tells you that x2 is 2. So that's already a done deal. Again, you get a particular value for x2 like you did in the homogeneous case. And then, of course, x3 is free, so that basically implies that x3 is just x3. So now what do we want to do? Again, we want to be able to write this solution. So that's already the solution done over there. But if we want to write it in the parametric vector form, then what do we have? So we have x1 as 4 over 3 times x3 minus 1, right? x2 is, I would say, 0 times x3 because there is no coefficient of x3 plus 2. So I'm trying to write everything in the uniform way. And then I have 1 times x3. Let's just write it for the sake of writing, because if you closely observe what am I doing, I'm trying to figure out the coefficients of x3 in each of the expressions. And then I'm also trying to figure out if there's a constant term. But quite clearly, there is none for x3, so you put a 0. And now if you want to write this in the column form, then you see that your x vector, which is basically x1, x2, x3, turns out to be actually x3 times the vector 4/3, 0, 1, plus a constant vector which looks like -1, 2, 0. Okay, so what do you observe with your solution over here? So if you closely observe, you already had x3 times 4 over 3, 0, 1. That was the solution to the homogeneous version of this system. So I still get that, and then there is this extra part. So this is the important conclusion over here, that this is your general solution from the homogeneous system, and then this is your particular vector or your particular solution. Okay, so you will so this is one very important thing that you should be able to come out of from here with, which is that your non-homogeneous system solution will always have the corresponding homogeneous one. Basically, what will that mean? The corresponding homogeneous version would basically mean that these are all zeros, right? So you will have the solution to that plus some particular vector, which will depend on this b vector that you have, right? So if I change this b vector in my system, then I will have a different vector here, and that's why it is called the particular solution for this system. Okay, so this is the important thing. So please make sure that, again, I really hope that you are able to see this extra portion or extra point that I'm trying to make about how the solution to the homogeneous version, the corresponding homogeneous version will always show up, okay? And then there will be the particular part. All right, so that is the whole scenario of having a homogeneous and a non-homogeneous system. Hopefully this is comfortable for all of you. In addition to this, I would suggest a couple of things that you quickly try. So one one thing that I definitely want you to think about is this practice problem 1. So extra, or definitely look at this practice problem 1 in section 1.5. So this is page 51 of the textbook. Okay, so please make sure that you try that. And then also look at how to, in section 1.6, there are 3 different applications. You can, so as an example, you can try to see how to balance chemical equations. Okay, so that's one application that we'll try to talk about when we meet. So how to balance chemical equations. All right, so I'll stop the video here. Hopefully this is helpful for you. And please do make sure that you try some extra practice problems. Thanks.